So the research that I do is related to, in general, a study, a field that we call, or a field of study that we call thermodynamics. Thermodynamics is generally the study of energy and entropy. We study energy converting technologies, things like solar cells and wind and steam power plants. And one of the key pieces of energy converting technology that we have is the internal combustion engine. And so more specifically, I study internal combustion engines. So this would include common day, everyday applications that we're familiar with, such as gasoline engines, diesel engines, natural gas engines, engines that power pipelines, compressor station, natural gas pipelines around the country, engines that power buses, automobiles, right, ships, so on and so forth. And also the same engines that we have in leaf blowers and snowmobiles, motorcycles, right? Engines are very ubiquitous. They're in several different applications. And so I study internal combustion engines, and I study them in the context of thermodynamics. I'm interested in the energy utilization. I'm interested in the efficiency losses, which is another way of evaluating the technology from the point of view of entropy and entropy generation. And some of the key specific things that we study in the context of internal combustion engines would be three main things. The first is the efficiency, as I've already mentioned, the ability of the engine to take some unit of energy and convert it into useful energy. And the second is what we refer to as performance. And this would be what most people have a sense or an appreciation of when they talk about engines, and that would be something like power, how much power the engine can make at a very given speed, operating condition, or in a particular application. And then the third aspect that we study is emissions. And of course, emissions has a direct impact on environmental quality, has an impact on air quality, air pollution, being able to meet what we call emission standards to ensure that that engine operates cleanly, produces that power not only efficiently but also cleanly, and mitigates the environmental hazards as much as possible. And so in this context of studying these three things of an internal combustion engine, which is driven by the desire, the motivation to study thermodynamics, we look at different types of combustion that we can have inside the internal combustion engine. We can have combustion that is very efficient but makes high amounts of emissions. We might have a combustion process that is very inefficient, which we don't like, but makes very low emissions. And so one of the key things when we study combustion is to try and have high efficiency and low emissions, basically maximize the one while minimizing the other. We also study different types of fuels. We know that we can use biofuels with engines. We can use different qualities of gasoline or different qualities of diesel fuels. And more specifically, we know that these fuels have properties that are more or less favorable to the combustion characteristics of the engines. And so we'll study different fuels, and we'll study how these different properties, these different fuel properties, affect the operation of the engine. And we do most of this work experimentally. We have engines in the lab that are running, that are burning fuels, that we're collecting data from. But it's also important to be able to do a lot of this analysis using computational methods, using theoretical models, right? Our theoretical engineering equations that we learn in our coursework, we directly apply those to studying internal combustion engines. And so I have a team of students that work at developing these models, being able to accurately represent the engine with, say, a computer simulation, a computer model, to be able to make all of these various calculations and then compare them and validate them against the experimental data that we have. Yeah, so I think the key feature that makes the research that we do fundamental is the fact that we're centered on a very fundamental parameter of say, the universe, right? The study of science. And that is energy, right? Energy is pervasive across the whole universe. We could also argue that the second parameter, which perhaps is even more fundamental than energy, is entropy. And so we know that energy is this ability for us to do useful things. Entropy is actually a way that, or is a measure that demerits the usefulness of that energy. And so when we look at studying any kind of energy converting technology, especially internal combustion engines, we always have to be mindful that what we're really studying is energy and entropy and the relationship that those two parameters have with each other, and particularly the negative influence that entropy has on energy in being able to convert that energy into useful work. And so that helps us keep our focus very fundamental, and of course also with the implication that it has on energy also makes the research very important. Energy, of course, is a limited resource, right? It's like water or food or any other type of resource that we have on the planet. And so we have to make sure that we utilize that energy as effectively, as efficiently, as appropriately, as responsibly as possible. And so our studies help us to ensure that we're using that energy appropriately and efficiently. Related to that, of course, is the other impacts that, again, any energy converting technology will have on the environment, and certainly including internal combustion engines. And so it's more than just the utilization of energy resources. It's also the utilization or the potential impact on other resources that we have on the planet, such as our atmosphere, right? And ensuring that we release as few emissions, as few toxins into the atmosphere as we possibly can to ensure that we conserve that resource, the atmosphere as a resource for us, so that we can continue to live and breathe clean air. Well, that's a great question. So how do I keep students engaged in the classroom? I think probably the first thing that I will always attempt to do whenever I'm teaching in the classroom is to make sure that we can make a relationship between what it is that we're learning in class on that particular day to how it impacts them as potential future, prospective future engineers. I view every student in the classroom as being a future engineer. They're engineering students, right? So it would make sense that that's the case. And it's critically important that as an engineer, we understand how we can arrive at solutions to problems that we're being asked to solve by relying on our fundamental principles. So all of these fundamental science and mathematical parameters and pieces of information that we learn in our basic science courses like physics and chemistry and calculus, and of course when you get into your engineering coursework, right, your what we call your engineering science coursework, this is usually years 2 and 3 of your engineering education. What we're really doing is we're learning the fundamentals of the study and practice of engineering. And if all you do is learn the fundamentals, it's very difficult to see or make a connection as to why that fundamental piece of information is essential to know as an engineer. Beyond just trusting the curriculum and trusting the course that we're being taught something because we must need to know it, I think it's really critically important to translate that information into something that is real for the student to have a relationship with. So for example, I teach thermodynamics, right? It's a common course for engineering students to take, and they're usually in their second year. And throughout the whole semester, I will always endeavor to make connections between that piece of information that we're learning in class that day to something which the student will have already had a relationship with, right? Maybe it's understanding how your refrigerator in your kitchen works, or maybe it's understanding how the air conditioning system in your car works, or maybe it's understanding how the furnace in your home works to heat your home in the wintertime, or how when you turn on the light switch, your lights come on because it's powered by electricity, which is being generated by a power plant somewhere. All of these different things, we as just everyday people have relationships with all of this technology, with all these applications. And it's very easy to associate that which we learn in a course of thermodynamics to these various applications. And so that's really probably the key thing that I'll endeavor every class period to do to engage students in the classroom. So there's relationships between fundamentals and technology, but there's also relationships between the student and the instructor, the professor. And I also think that's important for a satisfying and an engaging learning atmosphere. And so I'll always try to make a relationship in some form or another with students in the class. When you're working with a large class, that's difficult to do. As you can imagine, you have 100 students in the room and there's just one professor. So where I really take advantage of trying to get to know students and form relationships with them is when they come to office hours, right? And we get a chance to sit and chat one-on-one for a little bit and be able to learn, not just help the student with whatever questions they might have at that moment, but actually get to know something about them and what interests them and why they're studying engineering and what they hope to do with their engineering degree. For me, when I was a student, the most engaging classes that I had were with those professors who, I could form relationships with. And so that's also a very important thing for me to do when engaging students in the class. So that's a great question. What do I try to instill in graduates after they leave Texas A&M University? Well, Texas A&M actually makes this very easy for me to do as a professor. We have our Aggie core values. The Aggie core values: respect, excellence, leadership, integrity, selfless service, right? I think I'm missing one. Loyalty, right? So, these core values are basically our guiding principle that we want every single graduate of Texas A&M to exhibit, right? We want everyone that graduates from A&M to exhibit respect and excellence and leadership, loyalty, selfless service, integrity. So, what I try to convey in the classroom when I work with students and when I'm preparing students to graduate from Texas A&M is to really be dedicated to those Aggie core values. Really embrace them in your everyday everything, right? Whether it be, how you pay attention in the classroom, how you embrace a learning activity, whether it be in the classroom or outside the classroom, how you approach working with your team members on team projects, how you engage when you graduate with your employer, right? And you come to work every day, but even outside of, say, your professional life, right? Even within your personal life, the relationships that you form with people and these lifelong bonds that you'll construct. The Aggie core values just very beautifully summarize that which helps us to live good lives, right, and have lives of goodness. And so that's really, something that I, try to exhibit just even the way that I live my life with my students so that they recognize how powerful the Aggie core values can be. Beyond that, though, there's also another essential element that I try to impose in my students when they graduate, and that is a dedication to lifelong learning. This is really a really critical, aspect or virtue, if you will, to adopt, particularly as an engineer. It's really not right to think that any engineering school could teach any engineering student everything that they need to know in a matter of 4 years. Really what we most strongly endeavor to do from an engineering program is make sure that students know as many of the fundamentals as they will need to be successful practicing engineers. But there is a tremendous amount of information that we just don't have time or the resources or the opportunities to teach students in their 4 years of their engineering education. So in order for a Texas A&M engineering graduate to really have transformative impact on society, to really benefit society in a positive way, they have to be dedicated to lifelong learning. In other words, always be open and receptive to learning new skills, learning new ways of doing things, relearning your fundamentals, learning new ways of applying fundamentals to different applications, learning new ways of interacting with different people or people from different cultures, right? Just being ready to just embrace the wealth of information that you can learn as a practicing engineer. That dedication to lifelong learning will absolutely pay off in helping any Texas A&M graduate have a very meaningful and rewarding profession during their career. This is the easiest question. Great question, but definitely the easiest question. What do I love most about Texas A&M? I love the students. I've been to lots of different universities around the country. I've been to university myself. And when I was interviewing for a job, when I graduated with my PhD, and I was looking for positions in academia, faculty positions, I visited maybe 5 or 6 different universities for interviews. And I'll never forget when I first walked around campus at Texas A&M on my interview. We were taking a little walking tour of campus. And I lost count at the number of general congenial interactions that I had with the students of Texas A&M. I mean, of course, there were countless howdies, but people were holding doors open for me. People would just nod and smile. It was very clear that it was a friendly, warm, collegial, welcoming environment and atmosphere. And it was just clear that this was an attitude that the students just exuded, right? I mean, it was just part of their nature. It was part of their core being that the students here are just great. And so, of course, we also have exceptionally hardworking students here, right? And incredibly intelligent students, true scholars, right? The types of scholars that as a professor, you dream of being able to interact with the scholarly horsepower, right, to borrow an engine analogy, that we have here at Texas A&M, and it's all embodied in the students. So yeah, that's number one on my love list for Texas A&M is the students.